Okay, Chris, start it up. Okay, good, thanks. Hi, I'm Jim Scopolitas. Welcome to our second release on engine sensor basics. The two sensors we're going to look at today both have something to do with air. They're the oxygen sensor and the mass airflow sensor. In the videotape, I'm going to cover how each sensor works, how its signal affects the operation of the engine, and some general diagnostics, including trouble codes. For more specific diagnostics and some helpful tips, please refer to your technician's guide. Let's get started. An operating internal combustion engine takes in large quantities of air. The oxygen contained in air supports the combustion of fuel. Air drawn into the intake manifold contains about 21% oxygen. The air mixes with atomized fuel, and the mixture is carried to the cylinders where it is compressed and burned. We know that a ratio of 14.7 units of air to 1 unit of fuel delivers the best combination of high engine performance and low exhaust emissions. If the mixture contains too much air, the mixture is lean. There is more oxygen in the cylinders than is needed to burn the available fuel, so engine performance suffers. If the mixture contains too little air, the mixture is rich. There is not enough oxygen in the cylinders to burn all of the available fuel, so exhaust emissions are high. The challenge is to keep the air-fuel mixture in the correct ratio constantly and under most driving conditions. ECMs and PCMs use information such as coolant temperature, engine speed, throttle position, and the amount of air the engine is taking in to calculate how much fuel is needed at any given time. That calculation, even at its most accurate, is still only a prediction, which means it's not good enough to meet exhaust emission requirements. Catalytic converters can function properly only when the amount of oxygen present in exhaust gas is controlled within a tight range. A deviation from the correct air-fuel mixture as small as 1% can degrade catalytic converter performance and increase exhaust emissions. To get that last bit of accuracy needed, the ECM or PCM needs to know how each calculation actually worked out, and that's where the oxygen sensor comes in. By the way, instead of saying ECM or PCM all the time, I'm just going to use the word controller. When I say controller from now on, you'll know I mean ECM or PCM. The oxygen sensor is placed in the exhaust gas stream between the engine and the catalytic converter. There, it compares the amount of oxygen in the exhaust stream to the amount of oxygen in the air. The difference between these two concentrations of oxygen cause a small voltage to be developed in the oxygen sensor's element. That voltage is used to generate the oxygen sensor signal, which we call feedback. Because the amount of oxygen in the exhaust stream is directly related to the air-fuel mixture, the controller can use this feedback signal to continuously make small fuel delivery adjustments. In this way, it keeps the mixture at the ideal ratio of about 14.7 parts air to 1 part fuel. When the controller operates without feedback, we say the system is in open loop mode. When the controller operates with feedback, we say the system is in closed loop mode. 3 things are required before the system can go into closed loop mode. 1. Coolant temperature must rise to a specified value. 2. The engine must have been running for a minimum interval, typically 30 to 120 seconds. 3. The oxygen sensor element must be up to its operating temperature, which is about 600 degrees Fahrenheit. Once the element reaches operating temperature, the output from the oxygen sensor changes from high to low very quickly, many times per second. Keep in mind that the oxygen sensor senses only the oxygen in the exhaust stream, not unburned fuel. The controller, however, interprets that signal as mixture-rich or mixture-lean and responds with an adjustment in how much fuel it delivers. We can see how this works by examining the circuit. The oxygen sensor is connected to the controller and to ground with a single wire. The controller applies just under 500 millivolts to the circuit, and then it monitors the circuit voltage here at the input. This is how that same voltage looks on a simple graph. When the voltage seen at the controller's input falls within a narrow band extending slightly above and below this reference voltage, the controller reacts as though the signal has not changed. The controller reacts to the signal only when voltage falls below or rises above the band. Once it's up to operating temperature, the sensor develops a small voltage of its own. This can vary from about 100 millivolts to over 900 millivolts. With a rich air-fuel mixture, there is less oxygen in the exhaust. The less oxygen there is, the higher the oxygen sensor's voltage goes. When the sensor's voltage goes high, it pushes voltage at the controller's input above the reference band. The controller reads a mixture-rich signal. With a lean air-fuel mixture, there is more oxygen in the exhaust. As exhaust oxygen content increases, oxygen sensor voltage decreases. As sensor voltage goes low, it pulls voltage at the controller's input below the reference band. The controller reads a mixture-lean signal. The controller takes 80 oxygen sensor readings per second. Over time, it not only interprets each individual signal value, but also looks for trends. When the system is functioning normally, the controller sees signals about equally distributed between rich and lean. If the signal stays on the rich side of the scale without crossing the reference voltage line for too long, the controller sets a trouble code 45 and turns on the service engine soon light. On the other hand, if the signal stays on the lean side of the scale without crossing the reference voltage line for too long, the controller sets a trouble code 44 and turns on the service engine soon light. If the signal stays within the reference band longer than it should, with the signal between about 300 and 600 millivolts, that too indicates a problem. The controller sets a trouble code 13 and turns on the service engine soon light. It's rare for the oxygen sensor to give a false high voltage reading. So when the controller sets a trouble code 45, it typically means that the air-fuel mixture is in fact rich. To troubleshoot this condition, first use a scan tool to confirm that the code 45 is current and that sensor output voltages are trending above 600 millivolts. An oscilloscope pattern can also confirm that sensor output voltage is high. Next, perform fuel system diagnostics to find the cause of the rich mixture. Possible causes also include the mass airflow and throttle position sensors, the EGR valve, and a fault in the oxygen sensor ground circuit. I mentioned earlier that an oxygen sensor doesn't put out a usable signal until it reaches its operating temperature. A code 13 typically means that there's an open in the circuit between the sensor and the controller, or a failed sensor. Of course, it could also indicate that the sensor element is never getting up to its operating temperature. To check the circuit, disconnect the sensor wire. Measure circuit voltage at the controller. It should be close to the reference voltage. If it isn't, the circuit is most likely shorted to ground. Next, connect a jumper between the sensor wire on the controller's side of the circuit and ground. The voltage should drop close to zero. If it does, you know the sensor circuit is good. If it doesn't, there is most likely an open in the circuit between the sensor and the controller. Some oxygen sensors have 3 wires instead of 1. The 2 extra wires are for an internal heater that helps to get the sensor element up to temperature more quickly and keeps it there during all operating conditions. A trouble code 13 for this type of sensor could mean that the heater has failed. Oxygen sensors rarely fail outright. However, they are subject to surface contamination. Certain kinds of deposits can interfere with the sensor's operation and cause slow response time. Possible contaminants include the following: silica particles, lead, burned oil, and engine coolant additives. To remove an oxygen sensor, disconnect its wiring. Then use an appropriate wrench to loosen the sensor. If you have trouble unseating the sensor, run the engine for a few minutes to warm the exhaust manifold, then try again. When you install a new sensor, take care not to drop it. It's possible to damage the element. Screw the sensor in finger tight, then use a torque wrench to tighten it to 30 foot-pounds. If you're reinstalling a used sensor, first coat its threads with AC anti-seize compound. To control the air-fuel mixture, an ECM or PCM has to know how much air flows into each cylinder during the intake stroke. This can't be measured directly, but it can be computed using a mass airflow or MAF sensor. A MAF sensor measures how much air moves through the intake manifold. The controller can use that information to estimate how much air enters the cylinders for each combustion cycle. Airflow measurements are expressed in grams per second. A typical engine takes in about 5 grams per second at idle. That amount increases with RPM, engine load, and throttle opening until it reaches a maximum of about 150 grams per second. GM has used mass airflow sensors from 3 suppliers: AC, Hitachi, and Bosch. Since Oldsmobile does not use the Bosch sensor, we're going to talk only about the AC and Hitachi sensors. In any case, all 3 sensors use the same basic operating principles, which we're going to talk about next. For demonstration purposes, I have my own mass airflow sensor. Here, you see I've strung a wire between 2 terminals. This filter screen smooths out the airflow before it reaches the wire. In here is electronic circuitry that can send a variable current through the wire. Just like a real MAF sensor, I can monitor this current flow as well as the temperature of the wire and the temperature of the ambient air. It's about 20 degrees Celsius in here. That's equal to 68 degrees Fahrenheit. Let's send enough current through the wire to heat it to a point 75 degrees hotter than ambient, which would be 95 degrees Celsius. As you can see, the current required to do that is half an amp, or 500 milliamps. Now, with the wire temperature stabilized, I'll run this fan at low speed. That will simulate low airflow into the intake manifold as if the engine is idling. The airflow is cooling the wire. We're still using a 500 milliamps current, but the wire temperature has dropped from 95 to 80. I want that wire to be 75 degrees hotter than ambient, so I'm going to have to send more current through it. Okay, the wire is back to 95 degrees Celsius, and our heating current is now 750 milliamps. Let's turn the fan up to medium speed to simulate increased airflow into the engine. This causes a greater cooling effect, and again, wire temperature decreases. Again, I increase the heating current until I see the wire is at 95 degrees Celsius. You see the pattern? Each time the cooling effect increases, I increase the current to compensate. The same happens in reverse. If airflow decreases, there is less cooling effect and I can use less current. Now, what if the air temperature changes? Well, an air temperature sensor tells the control circuitry and it compensates with a new target temperature for the wire. The new target temperature becomes ambient air temperature plus 75 degrees, and the control circuits vary the current flow in the wire to match that target. If the air temperature dropped to 10 degrees Celsius, the MAF would decrease the wire heating current to attain a wire temperature of 10 plus 75, or 85 degrees Celsius. If the air temperature increased to 30 degrees, the MAF would increase current to attain a wire temperature of 30 plus 75, or 105 degrees Celsius. So, as the MAF sensor operates, it generates and monitors this constantly varying wire heating current. The sensor converts that information to a digital frequency signal the ECM or PCM can use. Now let's look at an actual AC MAF sensor. Here's the screen. Here's the wire, or rather the equivalent of the wire, a small circuit board with a thin film mounted on it. And in here are the electronics. The Hitachi looks different because it's part of the throttle body, uses a separate passage to place the heated wire, and instead of an actual wire, it uses a pair of resistors stuck into the airstream. Nevertheless, it works basically the same way as the AC sensor. The basic circuit for a MAF sensor looks like this. The sensor has 3 wires: power, ground, and a signal output to the ECM or PCM. If you see a MAF sensor with a 5-wire harness, that's a combination device with a manifold air temperature sensor built in. The MAF sensor still uses 3 wires. The remaining 2 are for the manifold air temperature sensor. Notice that the ECM or PCM puts a 5-volt reference on the line. The sensor generates a signal by alternately opening and closing a connection to ground. This toggles the line between 0 and 5 volts, producing a digital signal. The only way to see this kind of signal is on an oscilloscope. Here's a typical MAF output at idle. Notice how it varies. Low frequency at idle, high frequency at greater RPM and throttle opening. You can also use a scan tool to look at MAF signals. Keep in mind, however, that a scan tool displays grams per second values calculated by the controller, not the raw signal. A scan tool is the best way to check for trouble codes associated with the MAF sensor. These are codes 33 and 34. Code 33 indicates the ECM or PCM thinks the MAF sensor is reporting airflow that is too high as compared to other monitored conditions. Code 33 can result from an open circuit, either in the sensor harness or its connectors, from the sensor harness being routed too close to high voltage wiring, or from a faulty sensor. Code 34 indicates that the ECM or PCM thinks the MAF sensor is reporting airflow that is too low as compared to other monitored conditions. Code 34 can result from a short to ground in the sensor harness or its connectors, from the sensor harness being routed too close to high voltage wiring, or from a faulty sensor. In most cases, the engine will continue to run with a fault in the MAF circuit. The controller can use a default value as a substitute for the real MAF signal. Although the engine runs, the service engine soon light would come on, and you would most likely notice some drivability problems. To check a MAF sensor, hook up a scan tool and look for trouble codes. If you find a code 33 or 34, follow the instructions in section 6E of the service manual. If there are no codes and you have an oscilloscope, examine the output signal from the sensor. Confirm that the signal looks clean and changes appropriately with throttle opening and RPM. Examine the sensor harness and connectors. Confirm that the harness is well away from high voltage wiring. If these steps don't reveal the fault and you still suspect a MAF sensor problem, you may want to use this special Tech 1 cartridge. It's the MAF tester cartridge, and it comes with a cable and an attached MAP sensor. That's MAP with a P. The setup uses this MAP sensor as a reference during testing. The tester comes with a supplement for your Tech 1 operator's manual. This tester performs dynamic testing of the sensor with the engine running. It can test the Hitachi sensor used on 3800 engines and all AC MAF sensors except the one used on 3.8-liter turbo engines. There is one other tester available. This is the static MAF tester. It works only with AC MAF sensors, and it performs the test with the engine not running, ignition off. Be sure to follow the instructions for using this tester exactly. It's easy to condemn a good sensor by using bad procedures. The static tester is useful if you suspect an intermittent sensor malfunction. With the tester connected and the pass light on, lightly tap the electronics module of the sensor. If there is an intermittent malfunction, the pass light will briefly go off as the fail light comes on. Of course, you can also perform this tap test while you observe the MAF signal on an oscilloscope. Finally, problems in the intake system can create drivability problems that may appear to be MAF sensor malfunctions. Possibilities include an air cleaner obstruction, a leaking or blocked vacuum line, or a buildup of residue on the throttle plate. So don't forget to check these items if you want to fix them right the first time. I'm Jim Scopolitas, and I'll see you next time.